Close your eyes for a moment and imagine something with me. You are floating in the infinite darkness of space, surrounded by nothing but the cold emptiness of the void. The Earth, that beautiful blue marble you have called home your entire life, is now just a tiny dot of light behind you, barely distinguishable from the countless stars that surround you. You have travelled beyond the moon, farther than any human being has ever ventured before. The silence is absolute. There is no wind, no sound, no familiar sensation of gravity pulling you down. And then, without warning, your spacesuit begins to fail. A tiny crack appears in your helmet, and in that moment, everything changes. What happens next is something that scientists have studied for decades. And the truth is far more terrifying and fascinating than any science fiction movie has ever shown you. But here is the real question that should keep you awake at night. Why is it that your body, this incredible biological machine that has evolved over millions of years to survive ice ages, predators, famines, and diseases, cannot survive for even a few minutes in the environment that makes up 99.999% of our universe? Why is the human body so perfectly adapted to one tiny rock, orbiting one ordinary star and so catastrophically unsuited to everywhere else? Today, I am going to take you on a journey that will fundamentally change how you understand your own body and the universe you live in. We are going to explore the invisible barriers that exist beyond our moon. Barriers that no human has ever crossed and that currently no human can survive crossing. We are going to discover why the moon represents not just a destination, but a biological boundary, a line in the cosmic sand beyond which your heart, your lungs, your brain, your bones, and every single cell in your body begins to fail in ways you have never imagined. But before we venture into the darkness of deep space, I need to tell you some things that will blow your mind. Did you know that right now, as you watch this video, your body is being bombarded by radiation from exploding stars that died millions of years ago? These particles have been traveling through the cosmos at nearly the speed of light since before humans even existed, and some of them are passing through your body at this very moment. The only reason you're not dead is because of an invisible shield that most people do not even know exists. Did you know that astronauts on the International Space Station are actually aging slightly slower than you are right now, but their bodies are falling apart in ways that would horrify you? Did you know that there is a specific distance from Earth where the radiation environment becomes so hostile that we currently have no technology that can adequately protect a human being? Did you know that your blood would not boil in space the way movies show you, but something far stranger and more disturbing would happen instead? Here is perhaps the most terrifying fact of all. Between the years 1969 and 1972, 12 human beings walked on the surface of the moon. They are the only humans who have ever left the protective embrace of Earth's magnetic field. And during one of those missions, if the launch had been just a few months different, every single astronaut would have died from radiation exposure. They missed a lethal solar storm by pure luck. Nobody at NASA talks about how close we came to losing those astronauts to an invisible enemy they could not see, could not feel, and could not escape. So the question becomes this: if even reaching the moon was a deadly gamble, what happens when we try to go further? What happens when humans attempt to reach Mars, a journey that would take 6 months each way through the most hostile environment imaginable? What happens to your body when it leaves behind everything it evolved to depend on? If you have ever wondered why we have not sent humans to Mars yet, despite having the technology to build rockets that could get us there, the answer is not about engineering. It is about biology. Your biology. The rockets exist, the navigation systems exist, the communication technology exists. What does not exist is a way to keep the human body alive and healthy for a 2 to 3 year journey through deep space. And the reasons why will fundamentally change how you understand what it means to be human. Before we go any further, I want you to do something for me. Hit that subscribe button right now and turn on notifications, because what I am about to reveal will take you on a 90-minute journey into the most fascinating and terrifying aspects of human spaceflight that nobody talks about. And leave a comment telling me this: how far do you think you could personally survive in space? What would be the thing that kills you? Keep that answer in mind as we go through this journey together, because I guarantee your answer will change by the end of this video. Let us begin at the beginning, with a truth so obvious that we never think about it. You are, right now, living at the bottom of an ocean. Not an ocean of water, but an ocean of air. Every single moment of your existence, you have been submerged in this invisible sea of gases, with the weight of the entire atmosphere pressing down on you. 14.7 pounds per square inch. That is the pressure of Earth's atmosphere at sea level. Every square inch of your body is experiencing this pressure right now, and you do not even notice it because you have never known anything else. But here is where it gets fascinating. Your body is not just passively experiencing this pressure. Your body is built around this pressure. Your lungs expect it. Your blood vessels are calibrated to it. The fluids in your eyes are balanced against it. The gas dissolved in your tissues exists in equilibrium with it. Remove this pressure, and your body does not just experience discomfort. Your body begins to self-destruct in ways that are both horrifying and scientifically remarkable. Let us talk about what happens in the first 10 seconds after exposure to the vacuum of space. Forget everything you have seen in movies. Your body does not freeze instantly. You do not explode. Your blood does not boil, at least not at first, and not in the way you might think. What happens is far more subtle and far more deadly. The moment you're exposed to vacuum, the air in your lungs rushes out. If you try to hold your breath, which would be your instinct, the pressure differential would rupture your lungs and force air bubbles into your bloodstream, killing you almost instantly. So the first thing you must do to survive even a few seconds in vacuum is to exhale completely. Counterintuitive, terrifying, but necessary. With your lungs empty, you now have about 15 seconds of useful consciousness. During this time, something called ebulism begins. This is not your blood boiling. Your blood is contained within your cardiovascular system, and the pressure of your heart and blood vessels keeps it liquid. But the water in your tissues, especially near the surface of your skin, begins to vaporize. Your tongue would swell. Your skin would puff up dramatically. You would look like a grotesque parody of yourself, but technically you would still be alive. The actual killer in vacuum is hypoxia. Without oxygen, your brain begins to shut down within 15 seconds. You would lose consciousness, and if not rescued within about 90 seconds, you would die. Not from boiling, not from freezing, not from exploding, but from simple suffocation, as your body desperately tries to function without the one thing it needs most: oxygen. But here is the remarkable thing. Vacuum exposure is actually survivable if you are rescued quickly enough. We know this because of accidents. In 1966, a NASA technician named Jim LeBlanc was testing a spacesuit in a vacuum chamber when his suit depressurized. He was exposed to near vacuum conditions and lost consciousness in about 15 seconds. But because he was in a controlled environment, they were able to repressurize the chamber quickly. He survived with no permanent damage. The last thing he remembered before losing consciousness was the sensation of saliva boiling on his tongue. This tells us something crucial. The human body is remarkably resilient to brief vacuum exposure. The space between your skin and the external environment is not the immediate killer. The real killers in space are far more insidious, far more patient, and far more inescapable. And to understand them, we need to talk about something you have never consciously experienced in your entire life, but that has protected you every single second of your existence. You are living inside a force field. I am not being metaphorical. There is an actual physical force field surrounding Earth, generated by the liquid iron churning in our planet's core, and this force field is the reason you are alive right now. It is called the magnetosphere, and it is perhaps the most underappreciated phenomenon in all of human existence. Deep beneath your feet, roughly 2,900 kilometers down, lies Earth's outer core. This is a sea of liquid iron and nickel, heated by radioactive decay and residual heat from the planet's formation, and it is in constant motion. As this conductive liquid metal flows, it generates electrical currents, and these electrical currents generate a magnetic field that extends thousands of kilometers into space. This is the geodynamo, one of the most beautiful and complex phenomena in planetary science, and without it, you would not exist. The magnetosphere does something absolutely critical. It deflects the solar wind. The sun is constantly ejecting particles at incredible speeds, a stream of protons and electrons traveling at 400 kilometers per second or more. This is not gentle. This is a constant bombardment of radiation that would strip away our atmosphere and irradiate the surface of our planet if not for the magnetosphere. The magnetic field catches these particles and channels them around Earth, creating a protective bubble that extends outward about 65,000 kilometers on the side facing the Sun and stretches into a long tail on the night side. But there is a problem. The magnetosphere is not a perfect sphere. It has weak points, and there is a region where charged particles actually become trapped by the magnetic field, forming radiation belts of incredible intensity. These are the Van Allen belts, named after James Van Allen, who discovered them in 1958, and they represent the first major obstacle for any human trying to leave Earth. The Van Allen belts are not one thing. They are two distinct regions, sometimes three when solar activity creates a temporary third belt. The inner belt starts at about 1,000 kilometers above Earth's surface and extends to about 6,000 kilometers. This belt contains mostly protons, trapped particles from the solar wind and cosmic rays, and the radiation here is intense. The outer belt extends from about 13,000 to 60,000 kilometers, and it is dominated by electrons. Between them is a region called the slot, where radiation is somewhat lower. When the Apollo astronauts went to the moon, they had to pass through these belts. This is a fact that conspiracy theorists love to point to when claiming the moon landings were fake. How could the astronauts have survived the Van Allen belts, they ask? The answer reveals both the ingenuity of NASA engineers and the calculated risks that early space exploration required. NASA did not ignore the Van Allen belts. They planned trajectories that passed through the belts at their thinnest points. They used the slot region where possible. They kept transit time through the most intense radiation zones to about 30 minutes. The astronauts were exposed to radiation, certainly. Their dosimeters recorded it, but the exposure was brief enough that it fell within acceptable limits. They received radiation equivalent to a few chest X-rays, elevated certainly, but not lethal. But here is what nobody talks about. The Apollo missions were essentially gambling with the Sun. During periods of high solar activity, the Van Allen belts become more intense. Worse, the Sun can unleash massive eruptions called coronal mass ejections that send billions of tons of charged particles racing toward Earth. If a major solar storm had occurred during an Apollo mission, the astronauts would have had nowhere to hide. Their spacecraft offered minimal radiation shielding. They would have received lethal doses. In August 1972, between Apollo 16 and Apollo 17, the Sun unleashed one of the most powerful solar particle events ever recorded. If astronauts had been in transit to the Moon, or on the lunar surface during this event, they would have received a radiation dose of approximately 400 rem. For context, a dose of 400 rem is potentially lethal. It causes severe radiation sickness. Without intensive medical care, which would have been impossible in space, the astronauts would likely have died within weeks. The Apollo 17 astronauts launched 4 months after this solar storm. They had no way of knowing they had dodged a bullet that could have ended the entire Apollo program in tragedy and potentially set back human space exploration by decades. Luck. Pure, blind luck was a crucial factor in the success of the moon landings. Now let us take this understanding and zoom out even further. The Van Allen belts are frightening, but they are finite. Once you pass through them, you emerge into interplanetary space, and you might think, okay, the hard part is over. I am through the radiation belts. I am safe now. You could not be more wrong. The Van Allen belts are actually a symptom of Earth's protection, not a threat unique to space. They exist because Earth's magnetic field is catching and trapping dangerous particles. Once you move beyond the magnetosphere entirely, you lose that protection completely. You're no longer in a fortress where some radiation has accumulated near the walls. You're outside the fortress entirely, exposed to the full fury of the cosmic environment. Beyond the Moon, you enter a radiation environment that is qualitatively different from anything near Earth. You face two distinct threats, and current human technology cannot adequately protect against either of them. The first threat is solar particle events. These are the coronal mass ejections I mentioned earlier, plus solar flares and other eruptions from our star. The Sun is not a stable, constant ball of light. It is a churning nuclear inferno, constantly riven by magnetic instabilities that periodically release staggering amounts of energy and matter. These events are somewhat predictable, in the sense that we can see them coming once they start, but they are also random. We cannot predict exactly when the Sun will have a major eruption. When a solar particle event occurs, it sends a wave of high-energy particles racing outward at speeds that can exceed 2,000 kilometers per second. If you are within Earth's magnetosphere when this wave arrives, the magnetic field deflects most of it. Some particles get funneled down toward the poles, creating auroras, but you are largely protected. If you are on the moon when this wave arrives, you have minimal protection. The moon has no global magnetic field and essentially no atmosphere. If you are caught outside during a major solar particle event on the lunar surface, your only hope is to get inside a shielded habitat very quickly. The warning time might be only a few hours. But here is where it gets truly terrifying. If you are in transit to Mars when a major solar particle event occurs, you have nowhere to go. A spacecraft traveling to Mars is essentially a tin can with some aluminum walls. Aluminum provides minimal protection against high-energy particles. In fact, aluminum can make things worse through a process called secondary radiation. When a high-energy particle hits aluminum, it can shatter atoms and create a spray of secondary particles that are themselves harmful. You do not have enough mass in a practical spacecraft to provide meaningful shielding. You do not have time to get anywhere. You simply have to endure the radiation and hope it does not kill you. The second threat in deep space is even more insidious because it is constant. These are galactic cosmic rays, and they represent perhaps the single greatest obstacle to long-duration human spaceflight beyond the moon. Galactic cosmic rays are not from our sun. They come from the most violent events in the universe. Supernovae, the explosive deaths of massive stars, neutron star collisions, the supermassive black hole at the center of our galaxy. These cataclysmic events accelerate particles to incredible energies, and these particles then spend millions of years wandering through the galaxy until, by pure chance, some of them encounter our solar system. The particles in galactic cosmic rays are not just protons and electrons like the solar wind. They include the nuclei of heavier elements, stripped of their electrons and traveling at nearly the speed of light. Iron nuclei, carbon nuclei, oxygen nuclei. These are called HZE particles, which stands for high atomic number and high energy, and they are unlike anything your body has evolved to deal with. When a normal radiation particle hits your body, it ionizes some atoms, causes some damage, and your cell's repair mechanisms usually handle it. When an HZ particle hits your body, it does not just ionize a few atoms. It carves a track of destruction through your tissues. A single HZDE particle can pass through your entire body, leaving a trail of damaged cells in its wake. It can break both strands of a DNA molecule simultaneously, a type of damage that is extremely difficult for your cells to repair correctly. It can kill cells outright or, worse, damage them in ways that lead to cancer years later. Here is a fact that astronauts have reported since the early space missions. When you are in space, even with your eyes closed, even in complete darkness, you sometimes see flashes of light. These are called cosmic ray visual phenomena, and they're caused by HZD particles passing through your eyeballs and retinas. Each flash represents a particle traveling through your brain. You're literally seeing radiation damage occurring in real time. The constant background flux of galactic cosmic rays cannot be stopped by any practical amount of shielding. The particles are too energetic. To provide meaningful protection, you would need meters of material, and the spacecraft would become impossibly heavy. Water is one of the best shields because it is hydrogen-rich, and hydrogen is effective at absorbing some of this radiation. But even with water shielding, significant radiation gets through. Currently, NASA estimates that a round trip to Mars would expose astronauts to radiation levels that would exceed their lifetime career limits. We're not talking about minor elevated risk. We're talking about significant increases in cancer probability, potential cognitive damage, and other health effects that we do not fully understand yet because no human has ever been exposed to this environment for extended periods. Let me paint you a picture of what a journey to Mars would actually be like for your body, based on current technology and our understanding of the space environment. Day 1. You launch from Earth, and within hours you have left the protective embrace of the magnetosphere. You're now in true interplanetary space. The radiation monitors on your spacecraft begin recording elevated levels. Nothing immediately dangerous, but constant. A slow drip of damage accumulating with every passing minute. Week 1. Your body begins adapting to weightlessness. This is actually not adapting in a good sense. Your body interprets the lack of gravity as a signal that it no longer needs to maintain the same bone and muscle mass. Why waste energy maintaining structures that are not being used? Your skeleton begins releasing calcium into your bloodstream. Your muscles begin to atrophy. Your heart, which is a muscle, begins to weaken because it no longer has to pump blood against gravity. The fluids in your body redistribute. On Earth, gravity pulls fluids downward toward your legs. In weightlessness, fluids migrate upward toward your head. Your face becomes puffy, your legs become thin. More concerningly, the increased fluid pressure in your head begins affecting your eyes. The optic nerve starts to swell. Some astronauts develop vision problems that persist even after returning to Earth. Month 1. You are now deep in interplanetary space. Earth has shrunk to a bright blue dot, barely distinguishable from the stars. The psychological weight of this distance begins to press on you. When something goes wrong on the International Space Station, astronauts can be back on Earth within hours. An emergency return capsule can bring them home. When something goes wrong on the way to Mars, there is no return. The orbital mechanics do not work that way. You cannot just turn around. You're committed to a trajectory that will take months to complete, and no rescue is possible. The communication delay grows longer. At Earth-Moon distances, radio signals take about 1.3 seconds to travel each way. Annoying, but manageable. You can still have something like a conversation. As you travel toward Mars, this delay grows. At Mars distance, radio signals take anywhere from 4 to 24 minutes each way, depending on the positions of the planets. If you send a message saying you have an emergency, you will wait up to 48 minutes for a response. If the response is a question asking for more details, you wait another 48 minutes after answering. This is not communication as you know it. This is sending messages into the void and hoping for guidance. Month 3. You're now halfway to Mars. Something strange begins happening to the crew. This has been observed in long-duration isolation studies on Earth, and astronauts have reported it on extended missions. Around the midpoint of a long mission, motivation collapses, enthusiasm fades, depression and irritability increase. This is called the third quarter phenomenon, and it seems to be a psychological response to the realization that you have reached the point of maximum commitment. You're as far from home as you will get, and the journey ahead is just as long as the journey behind. Meanwhile, the radiation exposure continues accumulating. Your bone loss continues. Your muscle atrophy continues despite hours of daily exercise. Your vision changes continue. Every system in your body is slowly degrading, and you're still months from your destination. Month 6. You arrive at Mars. But arrival does not mean relief. Mars has a very thin atmosphere, less than 1% of Earth's surface pressure. This atmosphere provides essentially no protection from radiation. Mars has no global magnetic field. Some regions have localized magnetic fields from ancient volcanism, but nothing like Earth's magnetosphere. You're still being bombarded by cosmic rays and still vulnerable to solar particle events. The gravity on Mars is about 38% of Earth's gravity. This is better than weightlessness. Your body will function better than it did during transit. But we do not know if 38% gravity is enough to halt or reverse the damage that occurred during 6 months of weightlessness. No human has ever experienced extended time in partial gravity. We are operating completely blind. You spend 18 months on Mars. You cannot leave sooner because of orbital mechanics. Earth and Mars are only in the right positions for an efficient return trip every 26 months. You must wait for the planets to align. During this time, you continue accumulating radiation exposure. You live in a habitat that provides some shielding, but you must go outside to work. Every EVA is additional radiation exposure. Month 24, you finally begin your return journey. 6 more months of weightlessness. 6 more months of radiation exposure. 6 more months of isolation. This is now even more profound because you have already experienced the novelty of another planet, and all that remains is the long, tedious journey home. Month 30. You arrive back at Earth. You have survived the most dangerous journey in human history. Your radiation exposure over the entire mission is approximately 1 sievert, roughly 50 times the annual exposure of someone living on Earth. Your cancer risk has increased significantly. Your bones have lost 15 to 20% of their density despite countermeasures. Your muscles have atrophied. Your vision may be permanently affected. Your cardiovascular system has weakened. You step onto Earth's surface for the first time in 2.5 years and you cannot stand. Your body has forgotten how to function in gravity. You're taken by stretcher to a medical facility where you will spend months relearning how to walk, rebuilding muscle mass, and hoping that your bones will recalcify. This is not science fiction. This is the best-case scenario based on current technology. This is what we're asking astronauts to volunteer for. This is why human Mars missions have not happened yet despite having rockets capable of making the journey. But now, I want to take you somewhere even darker. Let us talk about what happens when things go wrong. On the International Space Station, which orbits just 400 kilometers above Earth, astronauts have experienced multiple life-threatening emergencies. In 2013, astronaut Luca Parmitano was conducting a spacewalk when water began leaking into his helmet. Within minutes, he had water covering his eyes, alarm filling his ears and entering his nose. He could not see and could barely hear. He was essentially drowning in his own helmet while floating in space. He survived only because he was able to feel his way back to the airlock, and his crewmates were able to get him inside quickly. On the Mir space station, a fire broke out in 1997 when an oxygen-generating canister malfunctioned. The crew fought the fire with extinguishers while smoke filled the station. They could not evacuate because their escape vehicle could only hold 3 of the 6 people on board. They had to fight the fire and win, or half of them would die. They won, but just barely. In 2018, a small hole was discovered in a Soyuz spacecraft docked to the International Space Station. Air was leaking into space. The crew patched it with epoxy and a finger while engineers figured out what had happened. Investigation suggested the hole was actually drilled during manufacturing and poorly patched. Then the patch failed in space. An industrial accident nearly killed astronauts. These emergencies happened within hours of potential rescue. Help was available if things got worse. Now imagine similar emergencies occurring not 400 kilometers from Earth, but 200 million kilometers from Earth. Imagine a fire breaking out on a Mars transit vehicle with no possibility of evacuation or rescue. Imagine a medical emergency, an appendicitis, a heart attack, a severe injury, with the nearest hospital 6 months away at minimum. Imagine a hole in your spacecraft when the nearest help is a light-speed communication delay away and no physical rescue is possible. The engineering required to make a Mars spacecraft reliable enough to survive for 3 years without major failures is daunting. Every system must work. Life support must function continuously. Oxygen generation, carbon dioxide removal, water recycling, temperature regulation, power generation, all must work for years without the possibility of spare parts or repairs from Earth. Any critical failure could cascade into mission loss. Mission loss means crew death. There is no other option. This brings us to something that is rarely discussed in the public conversation about space exploration. The ethics of sending humans on missions where rescue is impossible. On Earth, even in the most dangerous professions, we maintain the principle that rescue should be attempted. Firefighters enter burning buildings because rescue teams will come for them if they get trapped. Soldiers go into combat knowing that medical evacuation exists. Polar explorers file route plans so search and rescue knows where to look. For a Mars mission, we abandon this principle entirely. If something goes wrong, there is no rescue. The crew knows this before they launch. They are volunteering for a mission where the backup plan in case of serious emergency is death. This is not something we ask of people in any other context. It requires a fundamental shift in how we think about acceptable risk and human life. And yet, despite all of this, despite the radiation, despite the bone loss, despite the muscle atrophy, despite the vision damage, despite the psychological strain, despite the engineering challenges, despite the ethical dilemmas, humans want to go. There is something in us, some drive, some curiosity, some refusal to accept boundaries, that makes us look at these impossible challenges and say yes, but what if we tried anyway? Let us talk now about the solutions being developed, because the story of human spaceflight beyond the moon is not just a story of obstacles. It is also a story of ingenuity, creativity, and the relentless human drive to solve problems that seem unsolvable. The radiation problem has no perfect solution, but there are partial solutions that might make deep space travel survivable. Water is an excellent radiation shield because hydrogen nuclei are effective at absorbing and dispersing radiation energy. Some spacecraft designs incorporate water tanks as part of the hull, serving double duty as radiation shielding and a consumable resource. You would essentially travel inside a water jacket, protected by the very substance you need to survive. More exotic approaches involve active shielding, using magnetic fields or electrostatic fields to deflect charged particles. Earth's magnetosphere does this naturally. Could we create a miniature magnetosphere around a spacecraft? The physics works, but the engineering is incredibly challenging. The fields required would need enormous amounts of power and sophisticated superconducting magnets. It remains an area of active research. Some researchers are exploring pharmaceutical approaches. Could we give astronauts drugs that protect against radiation damage or enhance their DNA repair mechanisms? There is promising research on compounds called radioprotectants that reduce radiation damage when administered before exposure. Gene therapy might eventually allow us to enhance the natural radiation resistance of human cells. These approaches do not eliminate radiation risk, but they might reduce it enough to make missions survivable. The weightlessness problem has a more straightforward solution in principle, but it remains challenging in practice. Artificial gravity through rotation is well understood physics. If you spin a spacecraft, centrifugal force pushes everything toward the outside of the rotation, simulating gravity. This is not science fiction, it is basic mechanics. The problem is implementation. To create comfortable artificial gravity without disorienting Coriolis effects, you need a large rotation radius. The smaller the spacecraft, the faster it must spin, and fast spinning creates uncomfortable sensations and can cause nausea. A practical artificial gravity spacecraft would need to be enormous, or would need to use a long tether to separate the crew habitat from a counterweight, spinning the whole assembly slowly like a baton. Some designs propose partial solutions. Perhaps the crew sleeps in a small rotating section, getting a few hours of gravity each day, while spending the rest of their time in weightlessness. Perhaps a short-arm centrifuge allows exercise under simulated gravity. These approaches might reduce bone and muscle loss, without requiring the full engineering complexity of a completely rotating habitat. The psychological challenges are being addressed through careful crew selection, extensive training, and research into maintaining mental health during isolation. Astronauts on long missions are given regular private video conferences with family members. They are provided with entertainment, books, movies, games. They are trained in conflict resolution and group dynamics. But we do not really know if these measures are sufficient for a 3-year Mars mission. The longest single spaceflight in history is 437 days, by cosmonaut Valery Polyakov. That is less than half the duration of a Mars mission, and Polyakov could still see Earth clearly. He could still communicate in real time. He was not truly isolated in the way Mars astronauts would be. Some researchers are exploring pharmacological support for mental health during long missions. Carefully managed medications might help with sleep, anxiety, and mood regulation. But this approach has its own risks. Medication side effects in an environment where you cannot easily change prescriptions could be dangerous. And there are concerns about cognitive effects of long-term medication use in a situation where mental clarity is essential for survival. A more radical approach to long-duration spaceflight is induced torpor, essentially putting astronauts into hibernation for the transit phase of missions. Some mammals hibernate naturally, dramatically reducing their metabolic rate and surviving for months without food or water. Humans do not naturally hibernate, but there is research into whether we could induce a similar state medically. Lower metabolism would mean less food and water consumption, less psychological strain, and possibly reduced radiation effects since cells that are not actively dividing are more resistant to radiation damage. This remains highly speculative. We do not know if humans can safely be put into torpor for months at a time. We do not know the effects on muscle, bone, and cardiovascular health. We do not know if waking from torpor in a spacecraft millions of kilometers from Earth would even be possible. But it is being studied because the alternative approaches all have their own serious limitations. Now, I want to take you on a different kind of journey. I want to help you understand something fundamental about why this matters, something that goes beyond the technical details and touches on what it means to be human. You are the product of roughly 4 billion years of evolution, every single one of which took place on this planet. Your body is not just adapted to Earth, your body is Earth, in a very real sense. The calcium in your bones was forged in exploding stars, then incorporated into our planet, then cycled through rocks and water and organisms for billions of years before becoming part of you. The iron in your blood follows the same path. The water in your cells has been on Earth for longer than life has existed. You are not a visitor to this planet. You are an expression of this planet, a way for Earth to know itself. This is why space is hostile to you. You are asking Earth stuff to function in a non-Earth environment. Every system in your body expects conditions that only exist here. Your lungs expect a specific mixture of gases at a specific pressure. Your inner ear expects gravity to tell it which way is down. Your circadian rhythm expects a 24-hour light-dark cycle. Your immune system expects a specific microbial environment. Your psychology expects a certain range of social conditions, of horizons and distances and environmental variation. When you leave Earth, you leave behind the context in which every molecule of your body evolved to function. It is not that space is trying to kill you. It is that you are a highly specialized organism encountering an environment you were never designed for. A fish out of water does not die because the air is malevolent. It dies because the fish is a water creature, and its systems cannot function in air. You are an Earth creature, and your systems cannot function outside the narrow envelope of conditions that Earth provides. This perspective should fill you with awe, not despair. Consider the improbability of your existence. You live on a planet with a magnetic field strong enough to deflect solar radiation. You live on a planet with an atmosphere thick enough to maintain pressure and temperature in a range compatible with liquid water. You live on a planet at exactly the right distance from its star for that water to exist. You live in a solar system stable enough for complex life to evolve over billions of years. You live in a galaxy where the neighborhood is relatively quiet, without frequent supernova or gamma-ray bursts sterilizing everything. The conditions required for you to exist are so specific, so narrow, so improbable, that every moment of your life is a kind of miracle. The fact that the universe is mostly hostile to you is not a flaw. It is a reflection of how remarkable it is that you exist at all. You're a pattern of matter and energy that maintains itself against entropy, that repairs damage, that reproduces, that thinks and wonders and questions. You are the universe becoming aware of itself, and you exist in one of the only places in the cosmos where such awareness is possible. This is the true context for understanding why your body cannot survive beyond the moon. It is not a limitation to be resented. It is a reflection of your deep connection to this planet, your home, the only place in the known universe where beings like you have ever existed or could exist. But here is where the story gets really interesting, because despite all of this, despite our profound biological connection to Earth, we are still trying to leave. We are still building spacecraft, training astronauts, developing technologies to protect human bodies in environments they were never meant to survive. Why? The answer, I think, has to do with the same quality that makes us human in the first place. The same curiosity, the same drive to explore and understand, the same refusal to accept limits that led our ancestors to migrate out of Africa, to cross oceans, to climb mountains, to fly, to split atoms, to decode genes. There is something in us that looks at the impossible and sees a challenge rather than a barrier. Every human explorer who ever ventured into unknown territory faced dangers that would have killed them if things went wrong. The Polynesians who crossed the Pacific in wooden canoes, the polar explorers who trekked into frozen wilderness, the first aviators who lifted off in machines that barely worked. They all faced impossible odds, and many of them died. But some of them succeeded, and their success changed everything. The astronauts who will eventually travel to Mars, if and when we solve the technical challenges, will be the inheritors of this tradition. They will be taking the greatest risk any humans have ever taken, traveling farther from home than anyone has ever been, into an environment more hostile than any we have ever faced. Many things could kill them. Their bodies will suffer in ways we can predict and ways we cannot. They may not come back. But if they do come back, they will have done something unprecedented in 4 billion years of life on Earth. They will have extended the reach of life beyond its birthplace. They will have proven that the Earth stuff we are made of can, with enough ingenuity, survive in places Earth stuff was never meant to go. And this brings us to perhaps the most profound question of all. Should we even try? There are reasonable people who argue that human spaceflight beyond Earth orbit is not worth the risk and cost. Robots can explore space more safely and cheaply. They do not need food, water, or air. They do not suffer from radiation damage or bone loss. They do not get lonely or depressed. They can be designed for specific missions without the compromises required to keep fragile human bodies alive. Everything we want to learn about Mars, about asteroids, about the outer solar system, we can learn with robotic probes. Why risk human lives? This is a legitimate argument, and I do not have a definitive answer to it, but I can tell you what the counter-argument looks like. Humans bring something to exploration that robots cannot replicate. We bring adaptability, intuition, creativity. A robot on Mars follows its programming. A human on Mars can notice something unexpected and investigate. A robot has sensors designed for specific purposes. A human has the full range of human perception and human cognition, the ability to see connections that were not anticipated, to ask questions that were not programmed, to respond to the totally unexpected. More than this, humans bring meaning. When a robot sends back pictures from Mars, they are interesting. When a human stands on Mars and describes what they see and feel and think, it is transformative. The Apollo missions did not just collect moon rocks. They gave us the famous photograph of Earth rising over the lunar horizon, which changed how an entire generation thought about our planet. They gave us the words of astronauts who described the profound experience of seeing Earth as a fragile blue marble in the vast darkness. These experiences, these perspectives, these moments of human consciousness encountering the cosmos directly, have value that cannot be replicated by instruments. And then there is the question of long-term survival. Right now, all of humanity exists on one planet. A single catastrophe, an asteroid impact, a supervolcano, a pandemic, a nuclear war, could potentially end human civilization or even human existence entirely. We are, as a species, keeping all our eggs in one basket. If we could establish self-sustaining human populations on other worlds, we would dramatically reduce the existential risk facing our species. We would ensure that no single disaster could end the human story. This is not an argument for reckless haste. There is no urgent deadline forcing us to send humans to Mars before we are ready. We can take our time, develop better technologies, reduce the risks as much as possible, but it is an argument for continuing to work toward the goal, for investing in the research and engineering that might eventually make long-duration human spaceflight survivable. Let me bring this back to you personally watching this video right now. You live in an age of wonders. In your lifetime, humans have walked on the moon, built space stations, sent robots to every planet in our solar system, detected gravitational waves from colliding black holes, photographed a black hole directly, sequenced the human genome, developed mRNA vaccines in record time. The pace of scientific and technological progress in your lifetime has been extraordinary. It is possible, perhaps even likely, that in your lifetime you will see humans set foot on Mars. You may see the first humans born on another world. You may see the beginning of a truly multiplanetary human civilization. Or you may see setbacks, failures, tragedies that make us question whether the goal is worth pursuing. The future is not written. It depends on choices we make, investments we prioritize, values we hold. What I hope you take from this video is not despair about human limitations, but rather a profound appreciation for both the challenges we face and the ingenuity we bring to facing them. Your body cannot survive beyond the moon with current technology. That is true. But it is also true that every limitation humans have ever faced has eventually been overcome, transcended, or worked around through creativity and determination. We used to be unable to survive crossing oceans. We built ships. We used to be unable to survive in the air. We built aircraft and pressurized cabins. We used to be unable to survive underwater. We built submarines and diving equipment. We used to be unable to survive the vacuum of space at all. We built spacesuits and spacecraft. The same trajectory of innovation that brought us from caves to spacecraft can bring us from Earth to Mars and beyond. It will require solving problems we have not yet solved. It will require technologies we have not yet invented. It will require courage, resources, and the acceptance of risk. But none of this is impossible. Difficult, yes. Dangerous. Certainly, but not impossible. I want to leave you with one final thought. Everything I have described in this video, every danger, every limitation, every biological barrier between you and the cosmos, exists because you are made of Earth and evolved for Earth. This is your heritage, your connection to 4 billion years of life on this planet, your participation in the grand story of evolution. But you are also something new in that story. You are the first Earth life that understands its own limitations and can work to overcome them. You are the first Earth life that can contemplate the stars and dream of reaching them. You are the first Earth life that can ask whether life should remain confined to one planet forever, or whether it should spread and flourish throughout the cosmos. Whatever happens next, you are part of this story. The choices your generation makes about space exploration, about scientific research, about how we allocate our resources and ambitions will shape the future of life in the universe. That is an extraordinary position to be in. That is a privilege that no previous generation of humans has had. Your body cannot survive beyond the moon today, but your mind can reach everywhere the light of human curiosity can shine. And where minds go first, bodies have a way of following, eventually. Thank you for joining me on this journey through the most hostile environment humans have ever faced, and the most profound questions our exploration of that environment raises. If this video has changed how you think about space, about your body, about what it means to be human, I would be honored if you would like it, subscribe to this channel, and share it with others who might find it valuable. Leave me a comment telling me your thoughts. Would you volunteer for a Mars mission knowing everything you now know? What do you think is the greatest obstacle to human deep space travel? I read every comment and I'm genuinely curious what you think. There are more journeys like this waiting for us, more questions to explore, more mysteries to understand. The universe is vast and strange and mostly hostile to creatures like us. But it is also beautiful and comprehensible and ours to explore, one discovery at a time. Until next time, keep looking up, keep wondering, keep asking why. That curiosity, that drive to understand is perhaps the most remarkable thing the universe has ever produced, and it lives in you. Now, I've told you everything about why your body cannot survive beyond the moon. I've explained the invisible shields that protect you, the radiation that threatens you, the slow degradation of bone and muscle, the psychological strain of isolation, the engineering challenges of keeping humans alive in the void. I have shown you why the moon represents a biological boundary, a threshold beyond which our bodies begin to fail in ways we're only beginning to understand. But I have also shown you hope. I have shown you the ingenuity and determination that have already taken us from Earth to the moon and back. I have shown you the research being done to solve the problems that currently make deep space travel so dangerous. I have shown you that the same human spirit that drove us to explore every corner of our planet is now driving us to explore beyond it. The stars are waiting. They have been waiting for billions of years. They will wait a little longer while we figure out how to reach them safely. And when we do reach them, when the first human sets foot on Mars, when the first child is born beyond Earth, when life begins spreading outward from this tiny blue dot into the vast cosmic wilderness, we will look back at this moment in history and recognize it for what it was. The moment we stopped being a species confined to one world and started becoming a species that could go anywhere. Your great-grandchildren may live on Mars. Their great-grandchildren may live among the moons of Jupiter or Saturn. Farther in the future, perhaps centuries or millennia from now, humans or our descendants may spread to other star systems entirely. The same biological limitations I've described in this video will eventually be overcome, worked around, or rendered irrelevant by technologies we cannot yet imagine. But it starts here, it starts now, it starts with understanding why the challenge is so great, so that we can appreciate how great our response must be. This is the story of human space exploration, a story of unimaginable challenges met with unimaginable determination, a story of fragile bodies reaching for the stars, a story that you are part of, whether you become an astronaut or an engineer or a scientist, or simply someone who supports and encourages those who do. We are the universe becoming conscious of itself. We are stars that have evolved to contemplate other stars. We are the only beings we know of who can ask whether we are alone, and then build machines to help us find out. Your body cannot survive beyond the moon, not yet, but give us time, give us resources, give us your curiosity and your support, and watch what we can do. The best chapters of the human story are still unwritten, and some of them will be written in places far beyond the moon, in environments where nothing from Earth has ever survived before, by people who carry within them the same curious, restless, undefeatable spirit that has defined humanity since the beginning. That spirit lives in you. What will you do with it? End.